Hello everyone. Today we're going to look at summing exponential functions, and before we jump into that, we're going to pause here and take a look first at the geometric series. I'm showing here a page with some formulas. There's two general cases. One is when we're summing an exponential function. Here think of A as just being a general complex number. And in the first case, we're summing that over finite limits. So here m and n are just finite numbers. And then the other case that we'll look at is when one of the limits, usually the upper limit, goes to infinity. So let's take a look and think first about what happens in this first case. There's two cases here. One is, we distinguish the two cases based on the value of A. And essentially what happens here is when A takes on the special value equal to 1, so that's a complex number, no imaginary part, unit, real part, this sum basically simplifies a great deal. And all we have to do is count the number of terms in the sum, and then that becomes the value of the sum. So in that case, if you just count the number of terms between m and n minus 1, endpoints included, that turns out to be n minus m. It's n minus 1 minus m plus 1, and then the plus 1 cancels the minus 1. So we're just left with n minus m for that special case. And then for this case, when a is not equal to 1, let's take a closer look at that. And what we have here on this page is the series written out, all of its terms written out explicitly here with the dot 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 notation indicating the terms not seen. But each term in the sequence is a natural progression based on the previous term. Notice that each term increases, the exponent on A increases by 1. So there's no ambiguity here in just using the dot 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 notation. Let's also take that same sum and multiply every term in the sum by A. And essentially what that does is, if we were to write these out in a tabular form, it just increases the exponent on A in each term. So a to the m becomes a to the m plus 1. I've written that beneath this other a to the m plus 1 term, and so on all the way up to a to the n minus 1, and then a to the n. So this term a to the n minus 1 becomes a to the n. So everything shifts over by 1. What we're going to do now is subtract these two sums. And so here you see the first sum minus the second sum. And if we just subtract down, these terms in the middle cancel, and we're just left with two terms on the right-hand side. Now we can take one more step and factor out the sum from each of these terms, and that leaves 1 in the first term and minus a in the second term. And then if we, the last step is basically just to divide both sides by 1 minus a, and we're left with this form. You can see that if we multiply top and bottom by -1, it doesn't change the value, but it rearranges the terms. So you can use either one of these forms. I would encourage you to memorize this expression so that you don't have to rederive it every time you want to use it. One of the things that I'd like to point out about this is that in the answer we have a raised to the lower limit, and we also have a raised to the upper limit plus 1. So notice that happens. And again, that's because we did a times this term, so we get a to the n plus 1, or n minus 1 plus 1. And so that's the main thing that you have to remember in this formula. Now what we can do next is think about letting, say, the upper limit go off to infinity. When we do that, we have to think about what could possibly happen to this term here, a raised to the n, as n goes to infinity. And there's a couple of things to consider. So it helps if we write A in terms of its polar parameterization. So we'll write it in terms of a magnitude, a real positive number, r, and its angle, omega. And then if we raise that complex number to the n, we get the magnitude raised to the n, and then we have this exponential function or sequence here, which is oscillating. But so r to the n, this describes the envelope of that oscillation. And when r is less than 1, then we know that that envelope is decaying. When r is equal to 1, it's a constant envelope. And when r is greater than 1, it increases without bound. So only in the case, so if we look at this sum and let the upper limit go off to infinity, that's the limit as n goes to infinity. And if we just substitute and think about taking this limit, the only case where this limit is guaranteed to decay down to 0 is when the magnitude of a is less than 1. And so now we have this formula involving an infinite upper limit when the magnitude is less than 1, it applies. And then we can also consider another special case. This is probably one of the more common forms that we'll see when the lower limit is 0. So the sum from 0 to infinity of a to the n is equal to 1 over 1 minus a to the n, provided the magnitude of a is less than 1. Now what we can do is use those formulas to examine some sums. Okay, so the first sum that I'd like to do then is a sum over a symmetric interval. So we'll say we're going to start at negative n and sum up to positive n of e to the minus j 2 pi fn. Complex exponential sequence. Using the formula that we just learned, we can write that as we'll evaluate this exponential function at the lower limit. So we have e to the minus j 2 pi f of negative n. Then we'll subtract that from that, e to the minus j 2 pi f. And now we're going to add 1 to the upper limit and write that there. And then in the denominator, we have 1 minus e to the minus j 2 pi f. That's the answer. Now, if you have seen the video on the exponential integral, and whenever we integrate an exponential, we would get a sine expression and ultimately a sinc function. We'd like to repeat that sort of thing here. And what's required is that we have some symmetry in the arguments of the exponents. You see that we don't quite have the symmetry that we're looking for. So we're going to use the same trick here that we used previously. And I suppose I could make one small change here. I'll fix the negatives in that first exponential function. And the trick that we're going to use is to get symmetry in our exponents so that the sine function will emerge. The trick is that we're going to factor out of this difference an exponential which is whose argument is the average of these two exponents. So we'll have e to the let's see what happens when we compute the average of these two arguments. So we'll have j 2 pi f, and then we're going to average what's left. So we'll have n minus n, so that is 0. Then we'll have negative 1, and because we have two terms in the, we'll divide by 2. So it looks like I'll have minus j 2 pi f n over 2. Sorry, not n over 2, 1/2. So that's the term that we're factoring out. Let's see if we can see what is left after we do the factorization. So we'll have e to the j 2 pi f n plus 1/2. And then we'll have minus e to the minus j 2 pi f n plus 1/2. We better check that to make sure that we can recover what we started with. Now, if I multiply these two exponentials together, notice that I have 2 pi f times 1/2. Here I have e to the 2 pi f times negative 1/2. And so those 1/2s will cancel, leaving me with just e to the j 2 pi fn, which is here. If I multiply these two together, notice that here I have minus 1/2, and here's another minus 1/2. That gives me a total of negative minus 1 when I add those together. So here's minus 1, and so that checks out as well. Let's do the same sort of factorization in the denominator. I'll factor out the average of the exponents. So this exponent is 0, and if I average that with this one, that will just give me a similar sort of thing. In fact, I'll have e to the minus j 2 pi f 1/2. And if I split that out here, I'll have e to the j 2 pi f times 1/2 minus e to the minus j 2 pi f times 1/2. Again, we could check by multiplication that if we multiply these together, we'll recover the 1. If I multiply these two together, I'll recover this other exponential that we have here. Next, we'll notice that this ratio is equal to 1. Numerator and denominator are the same. And then what I have left here, let's examine this a little more closely. Notice that here I have symmetry in the exponents, and I have this first one minus the second one. So that looks like a sine function if I had a 2j to go with it. So this 2j and the top give me a sine function. And then down here in the denominator, I also have symmetry in the exponents, and that 2j together with this gives me another sine in the denominator. So writing that out, I have sine, I'm going to write it like this, pi f 2n plus 1. What I did is I multiplied this 2 in here, so I'll get 2n plus 1. And then in the denominator, I'll do the same sort of thing. I'll have sine pi f, and then these other exponentials cancel, so I'm done. A couple of things to notice here about this sum, this answer, is if you think about the original integral or sum that we started with, there are 2n plus 1 terms in this sum. And so that's the width of the interval over which we're summing. And that turns out to be a number that appears in the answer. And that's common. We'll see that over and over again. Another thing to notice, another skill to have, is to be able to sketch this sinc function. By the way, this is called a periodic sinc because it's a periodic function with period equal to 1. Notice that this is a ratio of 2 sines, which is a strange sort of a function. But notice that the sign in the top is oscillating more quickly than the sign in the denominator because we have the scale factor here inside the argument. So while this one goes through a single period, this one is going to go through 2n plus 1 periods. And so that's going to give us a function that would look something like this. Let's plot between 0 and 1. The denominator sine function is going to go something like that between 0 and 1. No, I take it back. Between 0 and 1, the denominator is going to go up and down. Half of a period of a full sine wave. And so the plot of this function is going to look something like a regular sine function where we will have 2n plus 1 periods, but the envelope is going to be modulated by the reciprocal of this function. So it's going to start high, then it's going to go low in the middle, and then go high again. And it would look something like this, perhaps. That would be one period of this function. Let's do another integral, or another sum, and then we'll take a look at a computer-generated plot. So this next sum that I'd like to do is a sum over a non-symmetric interval, e to the minus j 2 pi f n. Using our formula, we have e to the j 2 pi, e to the minus j 2 pi f times 0 minus e to the minus j 2 pi f times the upper limit plus 1, so that would be n, divided by e to the 1 minus e to the minus j 2 pi f. Again, we'd like to put this into a form of a periodic sinc function, so let's factor out the average, an exponential whose argument is the average of these exponents. When we do that, we'll have e, let's see, the term that we're going to factor out will look like this, e to the minus j 2 pi f n over 2. And so we'll have to have e to the plus j 2 pi f n over 2. We can check that by multiplication. Multiplying these two together gives us this, which is just equal to 1. Multiplying these two together recovers this term. We can do the same thing in the bottom. Here we'll have e to the j pi f minus e to the minus j pi f, and then e to the minus j pi f. If we check that by multiplication, this will recover a 1, and this will recover e to the minus j 2 pi f. So multiplying top and bottom by 2j will allow us to see the sinc function showing up explicitly, and I believe this is the form of the final answer. Once again, something to note here is that the width of the interval over which we're summing is equal to n, and we have an n showing up explicitly in our sinc function, our periodic sinc function, and in the exponent of this complex phase factor that's multiplying here, we get n minus 1. On the next page, I'm going to show you a plot just of this envelope, or this main periodic sinc function, just without the complex phase. And here I've plotted this for the special case when n is equal to 9. I've plotted this, first of all, over the interval from -1 to 3. So we should see 4 periods of this periodic sinc function, and in fact we do see that. I claimed that it had a period of 1, and it does. Also, the amplitude, the peak amplitude is equal to n. This is a log amplitude plot. Down here below we have a logarithmic magnitude plot in dB. And I guess there's a few other things that we could note about this function. If you count the number of zero crossings, 1, 2, 3, 4, 5, 6, 7, 8, 8 zero crossings in any period, and how many extrema are there in any period? Well, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8. So there are n-1 in general zero crossings and n-1 extrema in each period of this function. Let's do one more sum. We'll go through this one a little bit more quickly, but here's the sum I'd like to perform. This one would be completely general. And would include others that we've done as a special case. If we write this out, oh, actually, I'm sorry. I want to have -1 on as the upper limit. If we write this out using the formula, the general geometric sum formula, we'll have e to the plus or minus j 2 pi f a minus e to the plus or minus j 2 pi f b. What we do is we evaluate at the upper limit plus 1, divided by 1 minus e to the plus or minus j 2 pi f. Let's use our trick that we've learned about getting a symmetric exponent so that we can write it as the sine function. Let's factor out an exponential whose argument is the average of the arguments of these exponentials. When we do that, we'll have e to the plus or minus j 2 pi f b minus a over 2 minus e to the minus or plus j 2 pi f b minus a over 2. So there's the symmetric exponents that we were looking for. If we check that, I don't think we get quite what we want. I think I need to rewrite this as minus or plus on the first term and plus or minus on the second term. Now if you go through and multiply, this product will recover the first term, this product will recover the second term. Let's apply the same trick in the denominator. The piece that we're going to factor out is the average of the two arguments of the exponentials. And after we're done with that, we will have e to the minus or plus j 2 pi f 1/2 minus e to the plus or minus j 2 pi f 1/2. All right. The next step is I'm going to multiply top and bottom by -1. That fixes things up so that we have the correct form for our sine functions. And now if we write those sine functions down, we have sine of pi f b minus a, sine of pi f. We get a cancellation in the exponents of 2. And then we're left with the extra complex exponential. So here we will have plus or minus j 2 pi f. Actually, I'm going to cancel the 2 in the exponents as well. So I'll have pi f b plus a minus 1. And let's make a few observations before leaving this example. First of all, the width of the interval that we're integrating over is b minus a. That would be b minus 1 minus a plus 1. So that's b minus a, and that's the value that appears here in our periodic sinc function. Also, the value that appears over in our exponential phase factor is b minus 1, the upper limit, b minus 1, minus a, which is the lower limit. Okay, and using your newly acquired skills, you can now go off and make plots of this function. So doing it by hand, making a hand sketch is one thing, one skill, but let's talk about making a plot of this function in MATLAB. Unfortunately, MATLAB does not have, to my knowledge, a built-in periodic sinc function. It only has a built-in sinc function. And so we need to write our own periodic sinc function. To do that, let's consider how the MathWorks coded their sinc function. At the MATLAB prompt, if you type sinc and hit enter, it will show you the contents of the sinc script or the sinc function. And what I've done is I've cut and pasted that here for you to see how this works. Notice that the sinc function is pretty straightforward to evaluate. It's just sine pi x over pi x. But there is one special case that we have to worry about, and that is when x is equal to 0. And so in the code, inside this MATLAB sinc function, what we do is we have a couple of special cases here. The first, this code on line 3 uses the built-in find function to find all of those indexes in the input vector x, where x is equal to 0. And what we do is we set those equal to 1. You could set those to some other number. It doesn't have to be 1, as long as they're not 0, because what we want to do is avoid dividing by 0 here on line 5. So set those values to some other value, and then at those indexes, we will set the output equal to 1, because that's what the value of the output should be at that point, at those points. So let's mimic that style and write our own periodic sinc function. Here's an example of a function that I wrote. What we have to do for our function is think about the special cases. And so our sinc function, I'll say periodic sinc of x. We'll define that to be, in fact, we're going to need 2 arguments here. That will be sine pi x n divided by sine pi x whenever x is not equal to an integer. Because if you allow x to be an integer, we get sine of pi times an integer. That will give 0, and we need to avoid dividing by 0. Whenever x is equal to an integer, this function takes on the value of n. And so we're going to code our function like this. we're going to find all of those inputs where the input is equal to an integer. I'm using the mod function. I'm taking a mod by 1 to return where the array x is equal to an integer. I'm going to capture those indexes, and I'm going to set x at those points equal to 1/2, and I'm doing that just simply to avoid dividing by 0. Then I evaluate the sinc function, as you see here, and then at those points where the input was equal to an integer, I'm going to set the output equal to n. Here's a little bit of MATLAB code that shows how we can make this kind of a plot this kind of a function. So I'm picking a value for n. I am evaluating the frequency vector over a set of points from -1 to -3 in steps of 100th, and then I'm evaluating my newly created periodic sinc function. And the rest of this is just plotting. Let's see what that plot looks like. If you execute those commands, you'll see a figure window on your computer screen that looks something like this. So on the top you'll have a linear amplitude scaling plot. On the bottom you'd have a log magnitude scaling. As we expected, notice that the envelope of this sinc function is modulated by the reciprocal of sine of pi x, as expected. All right, last but not least, I have here a few homework problems for you to work on. I'd like you to do 3 different sums. Notice, as I say here, show your work, show the intermediate steps, follow the examples that I've shown. What I do not want you to do is just simply plug into the formula. Later you can do that after you learn the tricks, but I'd like you to learn and to practice using this strategy for finding a sinc function in the difference of complex exponentials, and that is to factor out the average, an exponential whose argument is the average of the exponentials that you're subtracting. So the 3 sums that I'm asking you to do is, one is a sum over a symmetric interval, one is a sum over a non-symmetric interval, and then the third is a sum over 2 disjoint intervals. I wish you good luck.